Hello, my name is Dr. Michael Okereke. Welcome to this channel. We are going to be looking at the modeling of a particulate metal matrix composite. So this composite material has got particles distributed within an aluminium matrix. The particle is silicon carbon and the matrix is aluminium. It's undergoing a tensile deformation, and we're going to recreate this kind of behavior. At the end of it, we're also going to extract the stress strain data from this. We're also going to generate the elastic properties of this material. This is the object of this video. Sit back and let's go ahead and consider how you can do this. Hello, welcome to CM Videos. My name is Dr. Michael Okereke. This is a YouTube channel where we try to help you get started with modeling. And if you're already down the modeling route and already been doing modeling, we also help you curate solutions to your finite element modeling problems. This video is aimed at RVE modeling, which is representative volume element modeling, and the focus is building on particulate metal matrix composites. A similar video which I put up in the card has also been made on RV modeling of unidirectional composite. If you've not seen that, please do click on the card and you would be able to see the video and see the same thinking that was used for unidirectional composite even for this one. So let's dive in and see what this video is about. So the first thing we need to say is this video has been requested. It's a video requested video session, and this is a video by Editor Tunbanjo, and he did say, great work doc, please can you do this for a particulate composite. So this is why I'm doing this video, to address this request from Banjo. Again, if you have ideas similar that you like me to make videos on them, please do put them and I would consider making them. If this is the kind of content that you like, please do subscribe to this channel and click on the notification button so that when content like this are made, you'll be the first to see them. Okay, so let's go ahead and think about the problem that we're dealing with today. So particulate composite. So this is a micrograph that I've taken from a book, from a journal paper, slightly older journal paper, and basically you could see a micrograph like this. So one of is 40%, 41% of silicon carbide with aluminium, and the other one is 45% of silicon carbide with aluminium. Different composition, but what you notice here is that the particles here are really the inclusion, and the kind of white, blobs across the structure is the aluminium composite. So this is a typical composite micrograph of an aluminium silicon carbide composite. So another example for the same, you could see these little circles there, or little squares here, are the particles, and then of course the regions around there are the matrix. So you could also see the same here. Again, this is another publication that I've taken this micrographs from. So this is quite common when you're trying to deal with particular composites. From micrograph, you see this kind of common representations. So what you will notice, having looked at that, is that the particle shapes can be quite different. So in most cases, it could be elliptical, ellipsoidal, plate-like, cylindrical, irregular shaped, like some of the ones we've seen, or even spherical. So the video today will be assuming a spherical distribution to this particular composite that we're modeling today. So what would the domain be? Our domain will be a 3D domain. It's going to be a 60 by 60 by 60 micrometer in dimension, cubic RVE, something that looks a bit like this. So where the grayish regions are the matrix, the aluminium, and the green region is basically the inclusion or the particle. So a particle will be a particle reinforced metal matrix composite with the reinforcement being a silicon carbide, the Young modulus for 10 gigapascal Poisson ratio. The aluminium is the matrix, again with the properties given, will allow the matrix to yield at 250 megapascal. The volume fraction of the inclusion, or in the fiber, in this case, the inclusion here is 20%, and the diameter of the silica is 20 microns. All right, so how many particles do you think will fit into this RV window? So we'll do a little calculation. So basically, we've got the window of length, width, and height, and each particle has a diameter d. So the volume fraction will be 4 pi d cubed over 8. So basically the volume of each of this circle sphere times the number there are in this window divided by the volume of the cube. And then if you rearrange the equation, you can calculate n. And for the system that we're dealing with, n is approximately 10 particles. So there will be 10 particles in that RV window, and that's what we're going to be using. Okay, so I have a Monte Carlo implementation that I use to randomly create this particle distribution. Again, please watch out the space. I would be making a video to show how this Monte Carlo implementation works. But basically, I'm using it here for a unidirectional for this particular composites, and you could see the distribution between the ones at the base and the one at the top. The color basically is a measure of the height where the particles are distributed. This was created in MATLAB. The dimensions are given, and the volume fraction obviously is the 20% that we want. So what we want to note also from this code is the positioning of each of the centers of the sphere, and this is what we have on the right hand side here. So the position of the center of the sphere. So this is the plan. So I'm going to create our RVE based on these positions of these inclusions. The other thing that we need to know is the case studies that I'll be studying. So I'll set a simulation for tensile deformation along the x-axis and a shear deformation on the xy plane, just for us to get a sense of how the model is going to behave following the situation that we're solving. So that's what we're going to do. So let's quickly jump over to ABAQUS so that we can begin the modeling. Okay, so here we are in ABAQUS. So let's go straight ahead and create the metrics. So our metrics would be 3D deformable extrusion. Okay, so the dimensions will be 0, 0, 60, 60. So that gives us the shape of the matrix. So we're going to extrude it to a depth of 60. So that gives us that. Then we'll do the particle. So let's just call it maybe particle. So call it particle is 3D deformable, but we're going to create by revolution. Okay, so basically, okay, so we could use this option. So what is the center of the arc is here. What is the coordinates that we want? 10 and 0. Okay, so we've got that. So we could do the same, basically 10 and 0 here. So we've got that. Then we need to close it up. Okay, so basically we've got that. So we need to now revolve it by 360 degrees. All right, so we now have our sphere. So it's a solid sphere, which is what the particle is going to be. So we leave that for now. And what we're going to do is, okay, so let's create a material. So our material here will be aluminium first. So we know that this aluminium will have a Young modulus of 75, e to power 9, and a Poisson ratio of 0.3. And then it's got a plasticity of 250, e to power 6, and a plastic strain of 0. Okay, so the other one we need to do is the Silicon Carbide, silicon carbide. So we know that the Young's modulus is 410, e to power 9, and 0.14, and that's all. It doesn't have any plasticity attached to it. So create the section. So what am I going to call this section? So my sections will be, okay, the alum section, aluminium section. So we call that, and then the other section will be silicon carbide section, SICCA section. Okay, so this is fine. Now we can associate the particles. So this is done, which is the silicon carbide, and then the matrix itself would be aluminum section. So this is fine. So we've got that. Now we go straight into the assembly. So we'll double click on the assembly. We'll create a particle together. Okay, so we've got the particle and the instances of that. So we could try different ways of showing this. Okay, so let's work with this view. Now what we have here is one particle. So what we need to do is that we need to distribute it randomly in that space. So I'm going to do a patterning of that, because there are 10 of them. There should be 10 particles. So you click done. So now I'm going to rotate it so that my particles form on the other outside. So let's again turn off perspective. So we have our particles this way. So maybe we can distribute it vertically. So which direction? Vertical. Okay, so this is fine. So I can take that off. So I'll just have more. Okay, now let's go in the X direction. Okay, so this is fine. So maybe we need to look at other views. Okay, so this is good. So what do we get? So fine, we have those views. So you could actually do this automatically, but because we haven't got a Python script for this implementation, so we're not going to do it. So we have this, okay, all this written 1 2 3 4 5 6, maybe 7 8. Okay, so how many do we have? 1 2 3 4 5. So we could, okay, so these are the particles. What I could do is I can remove the ones that are very much closest, so that, okay, so we remove that. So what we're going to now do is to move from here. So what we have is 1911 26, 1911 26. So I'm going to translate this one from the center to 1911 28. So it goes into the model 1911 26. Okay, so approximately that's not a problem. So let's look at change this to surfaces. Okay, so we could see that. So the next one is this, which is 50 37 31 50. Okay, from the center here, 50 37 31. So that goes into that place. To make sure that it's looking correct the way we want it. Okay, so that looks all right. So the next thing to do is to merge cut them. So I'm going to call this my PMMC. Okay, complete. So it's based on the mesh. So press retain intersecting boundary, select everything. Okay, so this is fine. So what is done here is that it's merged everything, created one instance. If we go back to the PMMC, is there. So I can go back and look at the instances. So it looks okay. Okay, so we could then do some work here, but before we do that, so what we are going to probably have to do is to trim off the domain. So if we go double click on that, so you click here, so I'll select one face, select that edge, okay, and basically trim off here. So it goes to this position, and then complete that. So that's done. Click through. Okay, so we go to the top, press that edge, select this edge, go to the other edge, select this edge, go to this other edge, and then click through. Okay, so let's make sure everything is fine. So we've trimmed off all the boundary fibers. Okay, so all the boundary fibers are trimmed. Now what we're going to do is to do the section assignment again. So you select the section assignment. Now I want, first and foremost, so let's probably hide. So let's show only the metrics. So if I select cell here, so I'll select only the metrics. Done. So that leaves only the fiber. So section assignment, select everything. I don't want to click that. Done. I want this to be the fiber or the inclusion, so that's fine. Then I invert that to reveal only the metrics. Aluminium section, select, this means select everything in the aluminium. Okay, then replace all, and then I can show materials. So the materials does show now that Okay, we have everything. So the particles are there, the materials are in place. So this is the right thing. So we can then mesh. So it's recommending 3, but let me probably double that just to make sure that I have a sizable mesh that that will converge very quickly, and then we can get this done. So I'll use a tetrahedron to mesh it, so everything is meshed in the form of a tetrahedron. So we've got that. So the next thing to do is that we need to create a set so that we can use that to apply our loading. So I'm going to call this my X front based on the node continuous. So I'm going to use by angle, 20-degree angle. So basically select all the node in front, X front. So the other thing that we need to do is again go back there and maybe say Z front, okay, based on the node. So we'll select everything in front there. So now if you go back to that, then we could open this up and just check. So that's the back, that's the front, that's Y base, that's Y top, Z back, Z front. Okay, so what we can do is let's query and find the position of this point. Okay, so if I query the position of that point, 60, 0, 60, 60, 0, 60. So what happens if I decide to create in the assembly module a reference point? So instead of here, I'm just going to put it somewhere around there. So that would be in the x-axis, maybe 70, 0, 60. So we've got a reference point there. Okay, still within the assembly window. Okay, we could create a set which I'm going to call my RP set. RP set. No. So in the assembly window, so RP set. Okay, and then we could select that. So that's the reference point set that we found. The domain is there. The material types can be seen clearly. So the other thing that we need to do is we need to set up an analysis step. So my loading step, so we could call this a loading step. So it will be a simple general static loading step. So this is fine. We need to create the history output. So for so reference point history output. So we call that, and then we have to do it based on the set of the RP. And I'll just say RF1 reaction force in the X direction, reaction force in the Y direction, reaction force in the Z direction, displacement in X, displacement in Y, and displacement in Z. So I just put those because I know that's what it is going to be. So now our constraint. So we're going to do the X-tensile. So X-tensile constraint. So let's do it this way. So X-tens constraint. We're going to use a star equation, and our star equation obviously would be based on the parameters that we have. So coefficient 1 here will be the RF in the front direction, degree of freedom 1 for X, minus 1, and the reference point goes here, degree of freedom 1. Okay, so we've linked this front face to that point so that when we apply load here, it will translate. So we could do that. So I'm going to say my X-tensile load based on displacement would have to be applied on the reference point. So what is my reference point? My reference point is this. Okay, continue. And this will be in the X direction, and our X direction is going to be, so it was a distance of 60, so maybe if we do 3, so let's just do like 5% displacement for this composite. So we're moving it in this direction. So the next thing to then do is to apply the boundary condition. So X back roller. So in the initial boundary condition, so X back would be this, so we could highlight that. So we're going to fix it in the X direction, correct? Now the Y base roller. So this will be fixed in the Y base, highlighted, will be fixed in the 2 direction of the Y direction. And then finally Z back roller. Okay, so if we then Z back, okay, and it will be fixed in the 3rd direction. So we've got our boundary condition, we've got our loading here. So we can then try and do the simulation. So PMMC extension simulation 1, if you want to call it that, and then you can submit that. So we'll submit that job and it will start running, and while it's running we can do the case for the tensor for the shear loading. Okay, for the shear loading. So what we're going to do is, if I go back here, I'm going to suppress all of that. So I'm going to suppress it. Okay, now I create a new boundary condition. So my X back will be now fixed because it's going to be in shear. So X back, okay, continue. So it will be fixed in X and Y, so allowing the Z direction to be free. Now X front will be a roller support because we are going to be applying load on the front. So continue. So it will be fixed in the 1 direction because we're going to apply load in the 2 direction. Okay, so we've got the back, we've got the front. Then we need our shear. So XY shear load. It will be based on a loading step, and I'm going to apply it on a reference point, and this reference point will be in the 2 direction, which, I mean, we could do the same 3 that we've done before, similar to the other case. So this is a displacement in the 3rd axis, in this axis. So back fixed, roller on the front, and then you have that. So then finally we need to sort out the constraints. So I'm going to suppress that, and then I'm going to say, okay, so we'll have XY constraint. Okay, so what will happen here is that 1, so we're applying it on the front face, but we are moving in the 2 directions. So this is XY. Now -1 reference point, but in the 2 direction. Okay, so now we could go ahead and double click on this PMMC XY shear sim 1. Okay, so we'll continue with that, and then we'll submit this. So now we've submitted both of them. They will run now, and then we can look at the results. So the first one has finished running, so we can look at the results for the first simulation. So you get some results. So what happens if we decide to exaggerate that and maybe make it 4? Okay, we could even go further, make it 6. So we now have a deformation profile. So let's reduce the speed, and then we watch. Okay, so this is fine. So I'm going to look at the viewport and remove some of, set that off and just leave the legend. And with my legend, I want to increase the legend value to maybe 18 or 20 so that it's more visible. Okay, and then I don't want this bounding box. Okay, so with the triad, I can increase the font on the triad to 20 as well, so that we have a clearer picture. And then if we look at, okay, the speed is fine. Okay, but what I always like to use is a plastic strain. Okay, so look at the plastic strain. The plastic strain gives you a better vision of what's going on in the model. So this is a simulation of tensile deformation in the X direction for this particular composite, and you begin to see some cool, really interesting behavior. So unlike the case of unidirectional composite, you are getting a full 3-dimensional behavior where the particles are there, they are kind of holding up and preventing deformation around them. I bet you somewhere behind this you will have a particle there. So if we cut that open, so in the other plane, okay, and then so if this is the front, so as you start moving in, so you can see this particle here is pushing against the neighboring particle, and then you end up with that. So yeah, so we could then look at the time-based case for this, What happens if we put the deformed and non-deformed together, and then it gives you again a picture of what's happening between the deformed case and non-deformed case. So if we continue to generate this and make it a little bit like 18.8, okay, so you get some really cool behavior. And this is what will happen with this material as it's deforming, using based as an RVE modeling of a particular composite. So this is slightly different from some of the things that I've seen on YouTube with people trying to do modeling like this, and they're just using simple domain. So these are kind of quite a complicated domain with very interesting boundary, richly style boundary conditions, and it gives you some really true three-dimensional response with the randomness of fiber positioning and things like that. So that's one thing we can learn from that. So the shear case is still running. Okay, so why not let's look at, while we're still on this, why not let's look at the history output. So we click on there, continue. Now this history output for extension, we would want the reaction force and the reaction and the displacements. We'll plot that. So you can see it gives us the reaction force and the displacement. Okay, so we click on, so we cancel this, click on that again, and then do some operation on that data. So we'll combine that. So if I combine displacement against force, plot the expression, then it gives you the force displacement trace for this particular composite. So you get a kind of an interesting prediction of elastoplastic behavior for this material. So what happens if we then look more closely into that to get stress strain data? So we use this Excel utility from current plot and click OK. So this will export your result into Excel. Hopefully you have Excel installed on your PC. So again, if I enter here, so this is displacement, this is RF1, so this is strain, and this is stress S11. So we know this is equal to the displacement divided by the gauge length of which is 60 micron. This will be equal to the force divided by the crossing area, which is 60 by 60. Okay, but I want to multiply by 1 e raised to power minus 6 because I want it to be in megapascal format. Okay, so we got that data. So if we then plot the two, insert, plot this data, so it gives you an interesting plot of this material. Okay, so whether you want it in this form or you want a different way, what we need here is the Young's modulus and the strength of this material. So how do we do that? So this will be equal to the slope of the stress value, comma, and the strain value, close. So I multiply that by 1 e to power minus 3, so that this answer will be in gigapascal, and this will be equal to the maximum in the absolute form of what you find in this case. So this will be in megapascal. So it gives you an idea of what's going on here. So for this unidirectional composite in the 1-1 direction, this is what you will get by the behavior. So you get a homogeneous yield strength, a Young's modulus of 21 or 22 gigapascal, and then the other of the strength is about 2274.6 gigapascal. So this is the effect of combining the two and generating some kind of interesting results for that. So the other thing, the final thing we need to then look at, okay, is the shear case. So we look at the results from the shear case is finished running. So again, you get some interesting shear behavior. So look at the view from the side, and then I'll change it to this case. Okay, so maybe, so let's still keep it in this window, and then we can animate that. Okay, so it basically gives us the kind of interesting result like we got with the other one, with the particle deforming similar to the other case. So if we then look at if I create a second viewport, and then I'll tile them vertically, okay, and then I'll link this viewport. So link the viewport, and then we could So the first one I'm going to change to tension. Okay, no, the second one becomes tension. And if we comment that, okay, so this becomes plastic strain. This is also plastic strain. Can I remove the viewport? So if I take away the legend, okay, so okay, maybe no, I'll leave the legend. It's okay. So we'll leave the legend. Okay, so we could yeah, look at what's happening, and then you animate them together, and then it basically gives you the behavior of the composite material in tension and shear. So this is the kind of result that I wanted to show. So if this is the kind of content that you like, please do subscribe to this channel and click on the notification button so that when contents like this are made, you'll be the first to see it. So thank you for your interest in the video. If again there are ideas about what you would like me to, videos you like me to make, please do suggest them in the comment section, and I would be happy to consider them and make them, just like I've made this video to support Banjo who requested for it. So thank you for again once more for your interest, and I'll see you in the next video. Bye bye.